Welcome to the wonderful world of physics. We're in the unit on thermodynamics. This is the beginning of chapter 17, the thermal behavior of matter. Matter responds to heating in several ways. It may get hotter, it may melt, it may boil, it may change size, shape, or pressure. In this chapter, we're going to explore the thermal behavior of matter. We're going to start by looking at gases and then move on to liquids and solids. So this lecture is 17.1 gases. It's been found several centuries ago for experimentation that for a gas, if temperature is kept constant, then pressure is inversely proportional to volume. So you increase the volume and pressure will decrease. You decrease the volume and pressure will increase. It was also found experimentally that if you keep constant volume, then pressure is proportional to temperature. So you increase the temperature and pressure will increase. And you think about aerosol cans, cans that might say a warning like do not incinerate or do not expose to extreme heat because the canister may explode. And that's because if it's a constant volume, then you increase the temperature, pressure increases, and it might explode on you. Also, it was found that for constant temperature and volume, if we keep both of those the same, then pressure is proportional to the number of molecules. So if temperature and volume are not changed in any way, the more stuff, the more material is in it, the more pressures they're going to be. I have a picture here to the right. It's a concept that we're going to think about in our studies of thermodynamics. It's a piston cylinder system. It's got a gas in it that I've colored blue right there. And the idea of the piston is this is a top that can be moved up or down. It can be manually moved. I put a little handle there up top, or maybe the pressure inside or the extra pressure on the outside will push that piston either up or down. So we're going to be thinking about a canister with gas. Now, from these three relationships, it was found this relationship right here, this is called the ideal gas law, and it's one we'll be using often. PV equals NKT, meaning for a gas, the pressure times the volume equals the number of molecules times a constant times the temperature. And the constant is K. It's known as Boltzmann's constant. It's in the front flap of your book. It's 1.38 times 10 to the negative 23 joules per Kelvin. And it's this equation that comes from those relationships that were discovered experimentally that will help us to figure out what is the pressure, what is the volume, what is the temperature, maybe how much material is in the canister. And when we change one or two of those variables, how will the others change? Let's look at that capital N right there. Capital N is the number of molecules. We will see related equations that use lowercase n, and lowercase n is the number of moles. So let's just keep that straight. Capital N, you can think of it as big N because it will be the big number. Generally, when we have a canister of gas, there are many, many molecules on the order of maybe 10 to the 23rd, 10 to the 24th, and so on. And we can also talk about little n, the number of moles. That'll be the smaller, the little number. So we have PV equals NKT, and sometimes you'll hear me say PV equals big NKT, which is the ideal gas law. Now, a mole. A mole is, when we do need a letter for that, we're going to use capital N sub A, and the A stands for Avogadro. This is Avogadro's number. It's 6.022 times 10 to the 23rd. And it's defined as the number of carbon-12 atoms in 12 grams of carbon-12. That's the definition of Avogadro's number. The relationship between big N and little n, the number of molecules and the number of moles, they're related by Avogadro's number. So you take the number of moles multiply it by Avogadro's number, and that gives you the number of molecules. And again, the number of molecules, because you're multiplying moles by a very large number, Avogadro's number, should be usually a pretty big number. Now, if you look down here where my pointer is, PV equals big N KT. I'm going to do a substitution here. Big N, the number of molecules, is equivalent to, as I wrote up here, the middle of the page, that's equivalent to the number of moles times Avogadro's number. So let's make that substitution. I've done it here in parentheses. Little n times Avogadro's number times Boltzmann's constant times T. Well, now the next substitution I want to make, you see what I've drawn here in the light blue, is Avogadro's number times Boltzmann's constant. Now, both of these are constants that will never change, but we multiply them together and we get capital R, which is the universal gas constant. This is another constant that's written in the front flap of your book. This leads us to another version of the ideal gas law. At the top of the page, you see PV equals NKT, and now it's PV equals nRT. But keep in mind the difference in the n's. PV equals big N, KT, number of molecules, and PV equals little n, number of moles, RT. So R, the universal gas constant, is Avogadro's number times Boltzmann's constant. We get 8.314 joules per Kelvin mole. Now, I've also written down below it another useful version of it, just in different units, in non-MKS units. It's 0.08205 liters atmospheres per mole Kelvin. And I recommend you write that in the front flap of your book, right next to the R that's written there, because it's useful. Sometimes we'll be doing problems and it's given in atmospheres and liters, and rather than having to do the conversion of atmospheres to pascals and liters to cubic meters, it might be convenient just to use this constant here. Let's look at an example in the book. And as we read through this example, we're going to have to discern which version of the ideal gas law is most convenient for us. So example 17.1 says what volume is occupied by 1 mole of an ideal gas at standard temperature and pressure. And it defines standard temperature and pressure. Temperature is 0 degrees Celsius and pressure is 101.3 kilopascals. So you can see I've written out the given information. It's asking what volume, so I wrote V equals question mark. And we need these in MKS units. And 0 degrees Celsius, we can't be using Celsius. We need an absolute temperature, or else our volume, when we plug it into the equation, is just going to come out to be 0. Even worse, if this were a negative Celsius, we would find ourselves with a negative volume. So we need the absolute temperature. We need kelvins, and so 273.15 Kelvin. That kilopascals, let's convert that to pascals, 101.3 times 10 to the third pascals. Because it's asking, or it's referring to the number of moles, we're going to use PV equals nRT with the little n that refers to moles. So PV equals nRT, we want to solve for V. There it is, V equals nRT over P. We're plugging in the values. Make sure that we're mindful of the units that they will divide out as necessary. So moles and moles divide away. Joules, well, we'll leave that there for the moment. Kelvin and Kelvin divide away. We're left with joules over pascals. And joules over pascals doesn't seem to divide into anything, but you can do dimensional analysis for yourself. Break down joules into kilograms, meters squared per second squared. Break down pascals. You know that pressure is force divided by area. Break that down, do the dimensional analysis, and convince yourself that joules over pascals is in fact cubic meters. We get an answer of 0.0224 cubic meters. That's the answer. If we want this in liters, it's good to know that 1 cubic meter is 1,000 liters. So I've done that conversion here, and we get 22.4 liters. So we think about this question. It's asking about gas. It's not particularly asking about air or hydrogen or helium or any specific gas. It's just about a gas. The nature of the gas never came into the question. It doesn't matter. What does matter is the temperature, the freezing point of water, and standard pressure. And so in those conditions, then a mole of gas is 22.4 liters. Now we're going to develop some further equations, and I want to get into the kinetic theory of the ideal gas. And particularly along the way, we are going to figure out why PV equals nRT, and figure out some other things, such as how can we figure out the speed, the typical speed of gas molecules. And so what we're going to do is apply Newtonian physics to molecules to derive the PV and T relationship. We're going to assume that there are many identical molecules of negligible size and shape. So just to make the math easy, we're going to assume that they are all the same type of molecule. We're going to assume that there's no action at a distance, no electrical attractions, for example, between them, and therefore no potential energy. We're going to assume that they're all moving in random directions, random speeds, and the speeds are independent of direction. So, for example, gravity is not going to be pulling down in one direction or another. Magnetic fields, electric fields are not going to be pulling in one direction or another. There's no preference for one direction over another. And that there will be elastic collisions with the walls, and therefore kinetic energy and momentum are conserved. So we look at this box right here. We're going to consider a large number of molecules, n molecules inside the rectangular box. And on this box, as you see, there is a length of it L, and that's the horizontal direction. We'll call that the x direction. And these molecules all bouncing around different directions, different speeds, and many of them at any given moment are going to be bouncing off the right wall. And so I've drawn that wall, I've shaded it in gray. That wall has an area of A. They're going to bounce off, they're going to bounce back, they're going to keep bouncing backwards and forwards. This is where pressure comes from. The gas pressure on the wall is from those molecules colliding against the wall. Now, just one molecule bouncing against a wall isn't going to make that much of a pressure, but if you have a lot of molecules constantly bouncing against the wall, they give that pressure. And remember, pressure is the average force exerted divided by the area. Let's, for starters, just consider one molecule. We'll deal with the n molecules later, but let's just think about one molecule as it collides against that rightward wall. Here you see up at the top, it's got some v velocity vector, and I have it going at some arbitrary angle. And notice it's got an x component to its speed and a y component, vx and vy. It's going to hit the wall and bounce off. Now, when it bounces off, Vy has not changed because in bouncing off that wall, there has been no vertical force exerted on it. Whatever speed it was moving in the y direction, it will continue. In the x direction, because of conservation of momentum and energy, remember it's an elastic collision, whatever x direction of speed it was going into the wall, it's going out of the wall. So it changes sign. It was positive, now it's negative. It exerts a positive force on the wall. The reason it changed direction was because the wall exerted a positive force on it. Those forces are equal and opposite. That's Newton's third law. Let's talk about now its change in momentum. Change in momentum is momentum final minus momentum initial. That change in momentum is completely horizontal because nothing changed in the vertical direction. So the final is negative mvx minus the initial, which is mvx. So its change in momentum is negative 2 mvx. Now, if we're talking about one single molecule, let's call it the ith molecule, or molecule number I, then the change in momentum of molecule I is negative 2 times the mass of V sub x for the ith molecule. Now, its V sub x will not change until it bounces off the left-hand wall. So it's going to keep on going. It might bounce off the floor, but that bouncing off the floor will change its vertical velocity. That's not going to change its horizontal velocity. So it will keep on going with that V sub x, and actually now it's negative V sub x, until it hits the left-hand wall. And then it's going to bounce, and sometime later it will eventually return to the right-hand wall. And it will do it in some time, and here we have some time increment for molecule I of twice the length of the box over whatever its horizontal speed is. So we're disregarding what it's doing in the vertical direction or in the z direction. We just know its horizontal speed is v sub x, and that's its speed. And in the time it takes to return to the right-hand wall, it's gone twice the length of the box because it's gone a complete lap. So that's the time increment. Now, again, as I wrote at the bottom of the page, we're not going to ponder, we're not going to worry about it bouncing off other molecules, because you look back at the assumptions that I wrote on the first page, it is not interacting. We're going to say there's sufficient space between the molecules. It's not going to be interacting with the other molecules. That's what happens with an ideal gas. Now, remember when it hit the right-hand wall the first time, it experienced a change in momentum. Here I just give the magnitude of it as of 2 mvxi. And now I'm going to add to that, whenever it hits the right-hand wall, that time increment goes by, it's going to experience that change in momentum again. And it delivers that much momentum to the wall. Now, Newton's second law says that the force on the ith particle is its change in momentum times the time increment. And we can say the average force on the ith particle is, and there's the change in momentum, 2 mvxi over, and here's the time increment, 2 times the length of the box over vxi. We clean that up, we can divide out the 2's, and we get mvxi squared over the length of the box. That's the average force on the ith molecule, but notice what I wrote here, average force from the ith molecule. Well, here I'm invoking Newton's third law. If that's the average force that the wall exerts on the molecule, then that's also the average force that the molecule exerts on the wall. And remember, what I'm developing here is getting into talking about where does pressure come from. So we're going to think about this in terms of the force that the molecule exerts on the wall. Okay, that is for the ith molecule. That's for a single molecule. But now let's talk about that this is a box full of n molecules. We're going to find the total force, which is the sum of that expression over n molecules. So the total force is the sum of all the average forces, which is the sum of this expression up here, vxi squared over L. In the summation, you can factor out the m over L, and it's the sum of all the vxi squareds. Okay, that's the total force. Now, pressure is that total force divided by area. So here I'm combining all those terms. Remember, total force was right where my pointer is, m over L times the sum of v squared. So there's my m over L factored out to the side, sum of v squared, and now I'm dividing by a. But look what I've circled right there. You have a times L, the area of the wall times the length of the box. That's the volume of the box. And so I've here turned it into volume, and we have m over volume times the sum of all the vxi squareds. Be careful with your own handwriting that you can distinguish your lowercase v from your capital V, because we've got two v's going on here. One is the speed or velocity of the molecules, and the other is the volume. Now, to further this derivation, what I've done in purple here, I'm multiplying by n over n, and why I'm doing that will become apparent very soon. So I've got the n up here in the numerator, I've got the n down here, so now the pressure is mass times the number of molecules divided by volume times this thing in parentheses. This is the sum of all the Vxi squareds for all the molecules divided by the number of molecules. So you can think of this as the average of the squares of the x components of the velocities. And we can notate that by writing Vx squared with a bar over it. Bar over a variable means average. So that brings us to this simplification. Pressure is mass times number of molecules divided by volume times Vx squared. We're getting there. Now, if you go back and look at the assumptions that I made on the typewritten page a few pages back, when talking about the ideal gas law, the third assumption was that speed is independent of direction, meaning there is no preference between the x direction, the y direction, the z direction, which means as I started this picture of the box, I drew it all going in the x direction. I could have just as easily drawn it all in the y direction or the z direction. It doesn't matter. And so if there's no preference between x, y, and z, then we can say that Vx squared bar is equal to Vy squared bar is equal to Vz squared bar. They're all equivalent. And now we're going to use a slightly more sophisticated version of Pythagorean theorem, which is that V squared is Vx squared plus Vy squared plus Vz squared. It's Pythagorean theorem in 3 dimensions. And if we add those all up, those three, and remember they're equal to each other, we can then say that V squared bar is 3 times Vx squared. Or another way of writing that, divide that equation by 3. Vx squared bar is 1/3 V squared bar. All right, so we have pressure equals Mn over volume times Vx squared. And I'm going to replace that Vx squared with 1/3 V squared bar. Here we have it right here. So we have pressure times volume is mass times N over 3 times V squared bar. And I want to take a moment, we're almost done with this derivation, but to compare it with the ideal gas law, PV equals NKT, and see how close it is. Well, we've got this relationship between P and V. On the right-hand side, we have N, and we have not KT, but something else. We have something involving the average squares of the velocities. Well, let's finish this up here. Let's multiply both the sides of the equation by 2 over 2, and we get PV equals 2/3 N times 1/2 mv squared bar. And that 1/2 mv squared, that should look familiar. That's kinetic energy, but it's got the bar over it. It's the average speeds. So that bit in parentheses is actually the average kinetic energy of the molecules. And now, as we're developing PV equals NKT, it's starting to come together, but we see PV, we see equals N times some other things. And those other things, there's a 2/3, there's a 1/2, and there is V squared with an M. And so you can see that somehow temperature is related to the average kinetic energy of particles. Now, in the ideal gas law, KT is then replaced by that 2/3 times 1/2 times mv squared bar. So 1/2 mv squared bar is 3/2 KT. So what we see is that temperature is a measure of kinetic energy associated with random translational motion of the molecules. Temperature is related to that average mv squared. So if you take this equation and solve it for V bar rather, you get what's called the thermal speed of the molecules. The thermal speed is square root of 3 kT over m. 3 times Boltzmann's constant times the temperature over mass. And that doesn't mean that that's the speed of every molecule. Remember, it really came from the average speed, and it's not quite an average, but you can think of it that way. It is, it's a measure of what the speeds of the molecules tend to be. We call that the thermal speed. Some molecules will be faster, some will be slower, but it's kind of like an average. Let's look at an example in the book that uses this equation, example 17.2. It says find the average kinetic energy of a molecule in air at room temperature, 20 degrees or 293 Kelvin, and determine the speed of a nitrogen molecule with this energy. All right, so we have the temperature 20 degrees Celsius or 293.15 Kelvin, and the question is asking to find the average kinetic energy. Well, average kinetic energy is 1/2 mv squared bar, which you saw on the previous page. That's the same as 3/2 kT. So we plug in 3/2 times K times the temperature, and we get 6.07 times 10 to the negative 21 joules. Now, if we want to know the speed specifically for a nitrogen molecule, which is N2, it's 2 atoms of nitrogen, the mass of a nitrogen molecule we need, well, a nitrogen atom is 14 atomic mass units. That's 7 protons, 7 neutrons, 14 atomic mass units, but we're dealing with 2 nitrogen atoms in the molecule, so it's 2 times 14 times the conversion for an atomic mass unit, 1.661 times 10 to the negative 27 kilograms, and we get that each nitrogen molecule has 4.651 times 10 to the negative 26 kilograms. We plug that in to this equation. Notice my arrow here. We just found out the kinetic energy, 1/2 mv squared. Let's solve that for v, velocity, square root of 2k over m, and we get 511 meters per second. Now, this is at room temperature, at normal pressure. So this is in the room that probably you're in right now. That is the typical speed of air molecules. That's about 1,140 miles per hour. So that's very interesting to note that even if the air seems to be still in the room that you're in, it's actually moving very fast. All those molecules are moving in random directions, typically at about 1,100 some miles per hour. But they're moving in all different random directions. Some are going slower, some are going faster at any given time. Since they're all moving in random directions, it all kind of cancels out and you really don't feel it. However, this is where pressure comes from. Now, I also want to point out, while I just took you through what I've written out on the screen in blue ink, in my handwriting, that's the solution as it's given in the book. I also want to point out, if you just want to get to what is the thermal speed, the quicker way of getting to it is just using that formula, 3 kT over m. You plug in those values. You still need to find the mass of nitrogen, but you plug in those values and that'll get you to the speed as well. James Clerk Maxwell, in the 1860s, he showed that elastic collisions among molecules result in a speed distribution that peaks near the thermal speed, but may extend much higher. And so this is what's called the Maxwell-Boltzmann distribution. And what we see here is n, which would be the number of moles, and molecular speed. Here we have 200, 400, 600, 800, 1,000 meters per second. And these are two different curves representing gases at two different temperatures. Let's look at for 300 Kelvin, and that is pretty close to a little higher than room temperature. We have the thermal speed, and notice, as I said, that it peaks near the thermal speed, but it's not exactly peaking at the thermal speed. The thermal speed is about more than 500 something. That's what we found in the last example. It was 511 meters per second for room temperature, so this is a little higher. But the number of molecules, the speed at any given moment that the number of molecules are moving is a little less than that, but still around 400 something. If you go to a much colder gas, 80 Kelvin, look at the red curve and look at the difference between the curves. We get a lower thermal speed, it's colder, so lower thermal speed, but it's not as wide. It's a narrower curve. And I also want you to see just from these curves that even though we have a thermal speed, which as I said is a typical speed that they're going, that there is a wide range of what the speeds are. However, as you see by the red curve, the cooler the temperature, the narrower that gap is going to be, or the narrower the curve is going to be. That concludes section 17.1 on gases. Have a great day.